MSc project, which is Machine Learning Methods to Solve Combinatorial Optimization Problem. Let's quickly go through the aims and objectives of this project. The aim of this project is to conduct a comprehensive literature review on existing applications of machine learning methods to solve combinatorial optimization problem and implementing machine learning methods for solving combinatorial optimization problem with a particular emphasis on the traveling salesman problem. The objectives are doing a thorough literature research on machine learning techniques used to solve TSP and other relevant combinatorial optimization problem. Use the appropriate machine learning tools and libraries to implement the graph pointer network architecture. Establishing a non-machine learning strategy as a benchmark for performance evaluation such as nearest neighbor approach. Generating appropriate traveling salesman problem dataset to train the GPN model and evaluating its performance on a dataset with a pre-existing optimal solution available on the internet. Using the supplied dataset, train and fine-tune the GPN model. Conducting comprehensive experiments to evaluate and compare the performance of the GPN model with the non-machine learning approach in terms of solution quality, computational efficiency, and generalization ability. Implementing a non-machine learning approach that is nearest neighbor to solve traveling salesman problem and evaluating its performance on already existing optimal solution and comparing its tool length. Drawing insightful conclusions from analysis and interpretation of the experiment's finding. Presenting the research result, including the advantages, drawback, and possible applications of machine learning techniques for solving combinatorial optimization problems. Let's begin with the machine learning approach to solve traveling salesman problem, which is graph pointer network. The components of graph pointer network model are the attention layer, the LSTM layer also known as long short-term memory layer, the graph pointer network, the training loop, and the testing part. Let's begin with the attention layer. The attention layer acts as a spotlight to guide the graph pointer network to the critical information. It consists of a query vector which stores GPN inquiry. It is like asking the question, which city should I go to next? Reference vector may hold the solution for this question. From the reference vector, the next city is selected. GPN scans and compares the component of the query vector with reference vector. It emphasizes the similar terms between these two vectors for decision-making process. Next, LSTM layer, which is also known as long short-term memory layer. So LSTM stands for long short-term memory. It remembers essential information from the past step. It then uses this memory for decision making. It consists of 4 gates, namely input gate, forget gate, cell gate, and output gate. Input gate. It is responsible for determining relevant new data. Forget gate. It discards any irrelevant information. Cell gate. It updates memory with fresh information. And output gate directs the next move. LSTM then creates new memory by fusing the input and past memory. Graph pointer network. It combines GNN, which is graph neural network, with attention mechanism and LSTM memory discussed earlier. The graph neural network GNN encoder is used by the GPN model. Similar to having different maps with different information, these maps are combined by the GNN to offer a comprehensive viewpoint and ensure the decisions are well informed. Based on this information, it then updates the hidden state. As the GPN progresses, more particular query vectors are created. The queries are directed at the pointer system, requesting advice on the next city to visit. It is analogous to a tourist requesting guidance from the natives. The GPN provides a probability distribution indicating how likely each city is to be visited. This is the result of the data processing and the memory usage. The city with the highest likelihood is chosen as the GPN's destination. Moving to the training loop. The dataset was generated randomly using NumPy library for the purpose of training the GPN model, where the generated dataset had 20 city coordinates in each sample. The dataset had a shape of batch size 2, where batch size was considered as 128 and size corresponds to the number of city coordinates present in the dataset, which is 20 in this case. As the training process, as the GPN model was trained on a dataset having like 20 city coordinates. The GPN forward pass is done for each city, selecting the next city to visit depending on the current city. Then the reward and policy gradient losses are calculated, which is part of the decision making process. Difference between achieved reward and a baseline reward is measured and is used to guide the GPN's learning process. To avoid unfavorable gradient exposure, gradients are computed with the help of the gradient tape and then clipped. With an optimizer, the model's parameters are updated using the clipped gradient. Additionally, a learning rate scheduler is used to dynamically change the learning rate while training goes on. This is to maximize the convergence of the model. Epochs and average rewards are displayed to monitor the training process. The cumulative tour length is monitored to provide insights in how effectively the GPN is improving. After the training time was recorded to be 7965 seconds, which is approximately equal to 2 to 2.5 hours, and where the number of epochs considered were 5 and the training step was 1000 and the batch size was 128. Moving on to the testing part. For testing the model, base29.tsp dataset from the TSP lib, which is available openly for the experimental purpose, is used. After testing the model on this dataset, the time recorded for testing is 0.60 seconds and the tour length obtained is 5.49 units. Since the GPN model was trained on a dataset whose value ranged between 0 and 1, the testing dataset is also normalized between this range. If we consider the list of index returned after training, which contains the order in which the cities are visited in the tour, and calculate the tour length using the distance matrix, the tour length obtained is 6476 units. The distance matrix is a matrix which contains distance between two cities. This distance matrix is also available in the base29.tsp dataset along with the city coordinate, which is the dataset used for testing this model. Moving on to a non-machine learning approach for solving traveling salesman problem, which is the nearest neighbor algorithm. This is the flow of the nearest neighbor algorithm. The algorithm starts. It then chooses the first city as starting city. Next, it finds the closest unexplored city and travels there. It would then check if there are any cities that are unexplored. If yes, then it would go back and again look for a closest unexplored city and travel there. If no, that means if there is no city which is unexplored, then it would check if it has accessed the first city. If it has not accessed the first city, then it would go back to the starting city, like which is the first city. And if the first city is already accessed, then the algorithm would stop. Here, the first city is always considered as the starting city, which has an index of 0. The algorithm is executed on base29 dataset from TSP lib. This dataset contains a pre-constructed distance matrix, which is used as a foundation for distance calculation. Let's move on to the output and evaluation part of the nearest neighbor algorithm. Euclidean distance is used as a measure between cities. After executing the nearest neighbor algorithm, the tour length obtained was observed to be 2258 unit, which is very close to the tour length of optimal solution, which is 2033 units. A very small execution time was observed, which is nearly 0.0009 seconds. Nearest neighbor provides fair but not always optimal solution. It serves as a rapid heuristic approach for solution generation. Let's have a look at the downfall while training the GPN model. Variation in tour lengths were observed during training due to limitations of computational resources. The model was trained using Google Colab's GPU server, which has time constraint over server access. Hence, as a reason, the training of the model was limited to 5 number of epochs and a step size of 1000. Increasing the number of epoch and step size will potentially improve the performance of the model. Due to existing hardware constraint, the GPN model could not perform to its full potential. Also, current implementation result in different starting indices of the city compared to that of the optimal solution, which impacts for a fair comparison and evaluation of the GPN model. Here, the output screenshot have been inserted. As you can see, initially when the training of the model begins, the tour length was observed to be 10.256 units. You can see the hyperparameters considered while training the model, where size, which is equal to the number of city coordinates, is 20 and the learning rate of 0.001 is considered. A batch size of 128 is considered and training step is equals to 1000 and the number of epochs are 5. But as the model trains and progresses with time and as it reaches to the last iteration, the training tour length observed is very less. It is 4.1396 units. So there is a drastic change in the training tour length, and as we can observe that the training tour length is decreasing with time. So this is a good sign indicating that the GPN model is training with time and it is improving its performance. Evaluation of the GPN model. Testing results. Tour length of 6476 units was obtained from testing on the base29.tsp dataset. This is significantly large compared to the ideal solution, which is 2033 units. Comparison consideration. The GPN model's inconsistent starting city affects direct comparison, as in the optimal solution for this base29 TSP dataset, the index of the starting city is always 0. However, the output which the GPN model gave, the starting city index is not the same. Hence, this comparison cannot be a fair comparison, because in order to compare the tour length, it is better if the index of the starting city is the same. Performance improvement scope. More iteration in epochs are likely to produce better outcomes, as the model is trained for different number of epochs and different training step. It was observed that the tour length value was changing. So there is a high scope of improvement of the performance of this GPN model if it is trained for a large number of epochs, good number of training step, and if a good GPU server is present, the computation, the hardwares are good. That's it.